Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Gamma Ray Bursts, Spectacular Explosions from the Distant Past by Giovanna Pugliese from the Anton Pankowick Institute at the University of Amsterdam. I am your host, Dr. Frank Summers from the Office of Public Outreach here at the Space Telescope Science Institute. And as always, I love to thank our wonderful tech team, Thomas Marufu and Grant Justice, who bring you these lectures every single month. Next month, on May 7th, Stellar Astronomy in Search of Dark Matter, how you can look at stars and find the dark matter out there. Eduardo Vitral of the Space Telescope Science Institute will bring that talk to you. In June, Nicole Arulananthan, also from the Space Telescope Science Institute, will talk about Webb observations of planet formation. This is one of the main science drivers of the Webb Space Telescope, planet formation, and she will give you the latest update. In July, the Pillars of Creation, multi-wavelength and in 3D. That will be me. I will be presenting on our latest three-dimensional visualization, this time of the infamous Pillars of Creation, and I'll have a blast presenting that to you in July. If you want more information, you go to www.stsci.edu/public-lectures, and you will find this web page. In the lower left corner, you can see links to our webcasts, both on our YouTube playlist and in our webcast archives at STScI. In the lower right, you can see how to sign up for our email. Enter your email address, hit that subscribe button, and you will get our monthly emails. Also on the website, we have the individual lectures descriptions, and if you click on one of those, you will get the full description of the lecture, as well as links to the STScI webcast, as well as the YouTube webcast. As I said, our email announcements, easiest way is just to sign up at our website. You can also subscribe to our YouTube channel, which is youtube.com Hubble Space Telescope. That's all one word, Hubble Space Telescope. And if you click on it, you will get the new video notices as well as reminders of live events such as this. And finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media accounts that we run at Space Telescope are for the Hubble Space Telescope, for the Webb Space Telescope, and for our Institute on Facebook, X, YouTube, and Instagram. And now the news from the universe for April 2024. And I chose just one topic to discuss with you tonight, the multi-wavelength views of NGC 604. Okay, let's start out at a broad view. All right, this is an amazing image by an astrophotographer named Malcolm Park. I want to give him great credit for it because it really it's evocative to someone like me who knows this part of the sky really well. Up in the upper left-hand corner is the Andromeda Galaxy, the nearest large galaxy to our Milky Way. It's also known as Messier 33. In the center is a bright star in the constellation Andromeda called Merak. And so this is one of the stars that actually you use to help find the Andromeda Galaxy. You go from the Great Square in Pegasus, you count up a couple stars, you get to Merak, and you say, just go over a little bit, and you find the Andromeda Galaxy on the night sky. But what I love about this image is it reminds me that on the other side of Merak is another galaxy in our local group. This is the Triangulum Galaxy, also known as Messier 33. So you're transferring from one side of this image is the Andromeda constellation, and on the other side of this image is the Triangulum constellation, and there are nearby galaxies in both of them. And the topic of the story this week is going to be inside Messier 33. So here is a view of Messier 33. While the Milky Way and Andromeda are large spiral galaxies, about 100,000 or a little more than 100,000 light years across, Messier 30 is what we call a medium-sized spiral galaxy. It's about 60,000 light years across. And this is a Hubble mosaic that contains about 1.3 billion pixels. Yeah, 1.3 billion pixels in this really, really large Hubble mosaic of Messier 33. And one of the cool things about it is that you notice in the upper right-hand corner, there is this really bright blue region there, and that is NGC 604. It is a nebula. And if I do show you a different Hubble image of that nebula, here is NGC 604 as seen by Hubble with the Wide Field Planetary Camera mosaic. You see, oh wow, this is a star-forming region. And you immediately start looking at it going like, okay, this is a nebula in our own Milky Way galaxy that just happens to be projected along the line of sight toward Messier 33. And you would be wrong because it is not. This is a nebula in the galaxy Messier 33, in the Triangulum galaxy. This nebula is 2.7 million. Yeah. So if I go back to that image, you can see just how big this star-forming region is. This is on the outskirts of the Triangulum galaxy, is a huge, huge star-forming region that we can see with this kind of clarity and detail from 2.7 million light years away. So this is obviously a target that if you're studying star formation, you want to study this. It kind of reminds me of the Tarantula Nebula in the Large Magellanic Cloud. It's one of these giant star forming regions inside the local group that we use to study star formation. And so here is what you see in visible light. You can see all the bright, massive stars, and you can also see the what we astronomers call warm gas. This is hydrogen gas that's heated to 3,000 to 10,000 degrees. Okay, so you've got massive stars and warm gas at thousands of degrees. Webb has now taken a look at this region, and in the near infrared, Webb's image looks like this. It looks significantly different because you're not seeing the massive stars. You're not seeing the biggest stars because they shine mostly at visible and ultraviolet light. The stars that shine primarily at infrared light are the lower mass stars. So you see the lower mass stars, and also you see what is called cool dust, dust that's at hundreds of degrees Kelvin, right? And so you're seeing a different set of dust. It's slightly displaced from where the visible light gas is. And then Webb also has a mid-infrared channel, which goes out to even longer wavelengths. And that you're seeing even cooler dust and seeing very few stars in the mid-infrared. Okay? So going from visible light to near infrared to mid-infrared shows you three different structures, three different types of structures inside this nebula. So they align them and put them together into this animated GIF. And so here we have visible to near infrared to mid infrared, visible to near infrared to mid infrared. And if you watch carefully, you can see the structure actually sort of expanding a little bit because you're seeing gas deep and dust deeper and deeper into the nebula. As you go to lower and lower temperatures, you have the gas and dust has to be further and further away from those hot stars in the core in order to be glowing at those temperatures. So in the visible, you're seeing the hot gas, and then in near infrared, you're seeing the cool gas that gets a little bit deeper, and in the mid infrared, you're seeing even a little bit deeper. And you're sort of watching the the structure, the skeleton of the nebula grow as you look further and into the dust. And this is one of my favorite things about living in the combined Hubble and Webb era, is that we really get to see high resolution, detailed images of objects like this that show us how they look across multiple wavelengths and see different facets of it with each image. All right, our speaker tonight is Giovanna Pugliese, and she is from, I gotta find, where's that stop button? There it is. Okay. And she's coming to us from the Netherlands, where it's 6 hours later than it is here in Baltimore. So thank you for staying up and giving this talk. It's fantastic. She's originally from Italy, and she got her undergraduate degrees at the University of Bologna and got her master's in Rome and got her PhD in Germany at the University of Bonn and the Max Planck Institute for Radio Astronomy. Then she traveled an awful lot, a good amount while doing postdocs, starting out at University of California, Santa Cruz. That must have been fun. The European Southern Observatory in Garching in Germany. And then she finally settled on the Netherlands and was at Utrecht University and Radboud University before settling up at the University of Amsterdam. One of the things I noticed while researching her on the internet today was that she has a strong commitment to teaching. She went back and got her master's in teaching. Okay, most astronomers who do research don't, I mean, they want to do their teaching well, but they don't go back to get a master's in teaching in order to do this. So, real big kudos to you for that. And
Thanks.
she tells me that one of the highlights of her life is her three kids. She has two twin boys and a girl, and that they are one of the highlights of her life, along with her husband, by the way, who is also an astronomer. All right. So, ladies and gentlemen, Dr. Giovanna Pugliese.
Thank you very much, Frank. It's really a big pleasure to be here for me, and I started to share my talk. And as I said, it's a really pleasure for me to be here because I can share with a large public my passion for astronomy. And I hope that at the end of this talk, people will know a bit more about the gamma ray bursts, what they are, and how they can be used as an amazing, fantastic tool not only to study the extreme physics of radioactive processes, that is emission of very high energy in really ultra relativistic environments, that is when matter is moving very close to the speed of light, but also as a tool to study the galaxies, the galaxy formation, the chemical evolution of galaxies very close to the Big Bang. So I am not the protagonist of this talk. The protagonists are gamma ray burst, and I think that is just better to start with them, just to show you how they look like in gamma. What are gamma ray bursts? They are just flash of very high energy in the gamma band that last for a very small amount of time. For many, many years, more than 30 years, this is just how gamma ray bursts looked to us. I tell you that on the horizontal axis, you have just the duration of this very bright emission in gamma, and on the vertical axis, you have the count of photons in the gamma detector. So you have just the energy that is released by these high energy photons in the detector. As you can see, I hope that one thing that is just striking you is that there is a large variety of GRBs. I would like to point your attention at the top right. You can see that the duration is just about less than 30 seconds, but then you see that you have a very sharp increase in energy, so in emission, and then slightly, very smoothly, it's just fading. Now, look on the bottom middle, you will see that the duration is just more or less the same, but it is a totally different feature that this new GRB is showing. So you have multiple peaks that gives the idea that the progenitor is acting in a different way. And then the question is, does this depend only on the progenitor? Does it also depend on the way in which this progenitor was formed or evolved or is interacting with the matter? So at the beginning, for, as I said, for many years, this is just what we were just wondering. And the reason it is because we could detect them only with the gamma detectors. Now, before telling you more about GRB, I would like to show you this plot. Probably many of you saw it already many times. To study gamma rays, we need satellites, because good for us and for our health, because the gamma rays are, they are produced in nuclear reactors. They are very bad for our health. So our atmosphere, luckily, is filtering them. As you can see, is filtering the gamma, is filtering the X. So to observe gamma rays and X-rays, we need satellites that are above our atmosphere. Then, of course, we have the optical part of the infrared. The microwave is also filtered. So we need telescopes that are above the atmosphere, and we are really very lucky to have JWST that now is doing great things for us. And then all the radio instead, they pass through the atmosphere, so we have a lot of radio detectors on Earth. What is another characteristics of the gamma detection? That for the way in which they work with a technique that is called scintillators. I don't go into details. Gamma rays, they don't give us a very detailed position. What does it mean? It means that when we observe in gamma, we have a lot of the portion of the sky. We have arc minutes. And so we cannot say to telescope on Earth, point there. It is like if I tell you that I have a friend in Rome, but I'm just telling you, okay, lives in Rome, but I cannot tell you in which street this friend is living. So for many years, we just observed gamma ray burst with the gamma telescopes. And what we know was just that they were very bright, emission in gamma and short duration. Then in the 90s, another telescope, another satellite with a better resolution was launched, and it started to observe the gamma ray bursts continuously. While there was some lack of time between the GRBs were discovered in the 70s, and then we started to get the data in the 90s. Well, the reason is a very interesting one, because the GRBs were discovered in the 60s by some secret satellites. So there were satellites, we were in the middle of the Cold War, and there were these satellites who were monitoring the nuclear explosions, reactions of atomic bombs that other countries were just testing, and United States was just looking in the sky to see what was going on. And suddenly they started to have all of this emission in gamma they were pumping out continuously, and they just realized that there were too many. They were everywhere in the sky, so they just realized they couldn't be terrestrial, they couldn't be really produced on the Earth, but they were astronomical. So for many years, until the 70s, we didn't know almost anything about these GRBs. Then in 73, we knew that GRB existed. And then, from when you decided to build a telescope until, or a satellite, until when the satellite is functioning, takes years. So our first detection for gamma ray burst astronomical detection was from BATSE, and it was an instrument on the Compton satellites in gamma, and Compton satellites through BATSE gave us three major information about the GRBs. If you look at this image, what is the thing that you note first? You know that GRBs are everywhere. This is just an image of how we see the sky from Earth, all of the sky. As you can see, GRBs are all over the places. We say that they are isotropically distributed in the sky. It means that they don't have a preferential direction. As you can see, they are not clustered in one place. They are all over the places. Another thing that BATSE observed for us, is that there was a less number of GRBs that were faint comparing to the number of GRBs that were brighter. What does this mean? This was a hint, an indication that probably gamma ray bursts were not occurring in our galaxy, but probably they were cosmological. Why? Because if they were on our galaxy, if objects are closer to you, you should also see more faint objects. The farther away they are, the less the faint you are detecting. And of course, Batze couldn't say anything anymore, because this was just the limitation of what the gamma detector could see. But there was another thing that through the data collected by Batze, we observed. We just observed that gamma ray bursts were just divided according to their duration in two groups. There were, as you can see here on the horizontal axis, there is the duration, and on the vertical axis, there is number of all GRBs observed. As you can see, there is a peak. It means that most of the GRBs are either below 2 seconds or above 2 seconds. And then, since this was published, we called the one below 2 seconds the short GRBs, short duration, and the long GRBs, long duration. What does this mean? Well, we could do speculations. Could this mean that they are actually two different classes of gamma ray burst, that they have different progenitors, or they have both different progenitors and they occurred in different environments, so in different galaxies? Well, we needed other satellites. We needed to observe GRBs in other wavelengths at other frequencies that could allow us to have a better position, a better localization of the event. Just to summarize, these are just the main observations that we had from until the 90s. We know that they were just publicly announced in 1973 that they peak in gamma, that the duration is between few milliseconds, that is, for example, 0.001 second, and up to 1000 seconds, that, as I show you in the previous plot, they can have a very rapid variability that we detected more or less from all over the skies, including short and long GRBs, about 1000 GRBs per year. And Batze discovered that they were isotropically distributed, and probably they could be a cosmological distance. Now, I would like to open a parenthesis, because I want to be sure that when I speak to you about redshift, about cosmological distances, and about parsecs, we know what we are speaking. So I would like, I hope that this goes, yes. Now, this is just a plot of how we think that our universe evolved from the Big Bang. Now, fix your attention on the bottom part of this slide. You have that on the bottom, you have the age of the universe. If you look at it on the right, there is the Big Bang, that according to the last cosmological data that we have and theory, we think that it occurred about 13.7 billion years ago. So if a Big Bang is 0, we are 13.7 billion years after the Big Bang. And then one way to measure this is through the redshift. The redshift, just to give you an idea, is just the Doppler effect applied to light. And it gave us a very good estimate according to some theory, modeling, and observations that are not part of this talk. They give us an idea of the expansion of the universe. This means that we are a redshift 0, and the more we go back in time, the more we go closer to the Big Bang, the higher the redshift is. And this is because, of course, as you all know, electromagnetic signal, that is light, photons, they have a finite speed, that is the speed of light. So light takes time for us to reach. When I'm going to speak about GRBs, I will tell you about the redshift, and when I tell you about the redshift, if the redshift is very high, I will give you the time from the Big Bang that this event occurred. But if it is a very low redshift, I will give you the distance in parsecs. Now, I don't know how many of you know what a parsec is. A parsec is a way in which is a unit of distance that we use to measure stellar objects, galaxies, objects in the universe that are further away from us. As we do during our daily life, and we do the same in astronomy, that is, we use different measurements, different units, according to what we are measuring. I'll give you a very simple example. If you want to measure a table in your kitchen, you don't use miles or kilometers. You will use either inches or centimeters or feet and meters. Well, we do something very similar in astronomy, but with other units. For our solar system, we use astronomical unit, AU. That is the unit that it gives the distance between us and the sun. That is 1 AU. But if we go into our galaxies, or if we want to measure the distance of other galaxies, as you can imagine, the AU is very teeny tiny. And I would like just to give you a very practical example so you can visualize, I hope, a bit how distant gamma ray bursts are. Now, do you know how far away it is the closest star to our solar system? Because our closest star is the sun, but the closest star to our solar system is called the Proxima Centauri, and it is a 1 parsec. Now imagine that you are at home and you take a step, and taking that step, that corresponds to 1 AU. So taking that step, you reach the sun. How many steps or how many miles do you have to take to reach Proxima Centauri from your home? What I mean is that if making one step, you just reach the sun. Proxima Centauri is, I don't know, in your living room, or it is next door to your neighbor, or it is to the supermarket closer to you, or the next city. Well, if with one step you're home and you are in New York, you reach the sun. To reach Proxima Centauri, you have to go from New York to Philadelphia. It is about 100 miles. And it's just 1 parsec. So with one step, you are at the sun. With 100 miles, you are in another city and you reach Proxima Centauri. In Europe, consider that if you are in Rome, then to go to Proxima Centauri, you have to reach more or less the north of Naples. That it is 144, 150 kilometers. So I hope that now we know, when I'm going to speak about distances, how we can just quantify and visualize this. Let's go to the next step. This is just what happened in 1997. Just to clarify, when we name a GRB, there is first the year, then the month in which occurred, and then the day. So this was the first ever GRB observed in the optical. It was the 28th of February 1997. Why we were able to do all of this? Well, because in 1996, BeppoSAX, that is a satellite in X-rays, a collaboration between Italy and the Netherlands, was launched. Why in X-rays? Because in X-rays, eventually we can have a more narrow position to give to the telescope on Earth and say, look, now it is not anymore arc minutes, I'm giving you arc seconds. It is like if now I'm telling you that my friend not only lives in Rome, but I'm giving you the address of my friend with the street and the civic number. And this is what happens in February 97. BeppoSAX had got a trigger. He got to the position, he took this position and he shared with a lot of different detectors and telescopes on our planet. This is a Dutch telescope on Canary Islands, and the telescope now knows where to point, and it could observe the first optical transient of GRB. And then they saw that it was cosmological, because look at here, it was 0.69 the redshift, and this corresponds to about 7 billion and 400 years after the Big Bang. So the light really spent more than 6 billion years to reach us. And this was the first amazing evidence, not only that GRBs are cosmological, so they are not in our galaxy, that they are in other galaxies further away from us, but also that they are emitting energy in gamma, in X-rays, and now they are also in the optical. And that was starting to be interesting, because this means that we have something very powerful, very energetic, that still has energy to radiate not only in gamma and X, but still in the optical. And then gamma reversed 970508 occurred. This is the one of the 8th of May 1997, and this is an HST image, and this was an amazing proof that GRBs are cosmological. But not only this GRB taught us a lot of things. First of all, you can see that on the left there was the first image taken by HST, that is not optical. And then on the right, you see that after a few days, the brightness of the image is starting to fade. But together with this, also radio telescopes pointed on the direction of this GRB, and they saw for the first time that the GRBs also were emitting in radio. So at this point, you are starting to have a lot of pieces of a puzzle all together. It is very bright. It is very, very energetic. It has a very short duration and is emitting in so many electromagnetic waves. So what this is? You have to think that, at least I like to think in this way, that in science in general, we have a kind of tennis match between the theory and observations. Sometimes the theory can make predictions of what later on, with good, better instrumentations and the evolution of technology, we can observe. And this happens all the time with Einstein and all what he theorized. And that he did some predictions, and then we see, oh wow, that's true, that is there. And then what happens? That then when you have the data, you are again launchable to the theory, saying, okay, this is something new. Theory, can you explain this? Sometimes the theory can, sometimes can't, then we have to tune it. And then it is just going on a kind of bouncing between theory and observation, just to improve our knowledge of whatever we are researching. In the case of astronomy, of course, astronomers is, of course, the universe. In the case of GRBs, the prediction was there. It was done in the 80s with something that is called the fireball model. Now, if you go online, you find really a lot of simulations about this. But I will try to use my hands to explain. The idea is the following, that long GRBs are associated with the explosion of supermassive stars, that is masses that it is at least 20, 30 times the mass of the sun. While the short GRBs are related with the merge of compact objects. At that point, we didn't know if it was two black holes merging, or a black hole and neutron star, or a neutron star, or together with another neutron star. But whatever is the progenitor, either two compact objects or a supermassive star, gamma ray bursts are just the fireworks that the universe is launching toward to us, saying, hey, look at here, a black hole is born. These are what gamma ray bursts. This is what gamma ray bursts are. They are just the birth of black holes, stellar black holes. The idea is just the following. Let's focus more on the long GRBs because they are a bit, at least for decades, they were better studied than the short GRBs. Now imagine that you have your supermassive star. You know that it's just starting with wind to spread matter around itself in the 100,000 of years that is its life. And then at a certain point, the radiative pressure is just not anymore supporting gravity. Gravity is taking over. The core is just shrinking, and is collapsing. While this core is collapsing, the idea is that it's forming a black hole in a way in which we cannot yet tell you, because this is just something we are working on. This is work in progress. Two jets, one opposite to the other, are launched. So when the black hole is formed, two jets are launched. These jets, what are? They are just channels, very narrow channels of super-relativistic matter and energy. And we see the GRB if these channels are just pointing to us to our telescopes. Once these jets are launched, the star is still, the black hole is still there, but the matter is still collapsing, and then it explodes as a supernova, what we call an hypernova. Now, what happens in the jet? Focus on the jet. In the jet, we have this super energetic matter, ultra relativistics, that is the speed of this matter is very close to the speed of light. Then you have what we call shells of matter. Imagine just the layers of an onion. So you have these shells of matter that are moving, but sometimes their speed is in a way that one shell is just hitting each other. So you have gamma, gamma, gamma. Then it started to decrease because it started to expand. And you have X-rays, X-rays. Then this jet, this channel of matter is entering into the circumstellar medium. When it is entering, it's just like when you are entering a street with the traffic, you have to decelerate. So you have gamma, gamma X-rays starting to decelerate, enter into the circumstellar medium, and then you have optical, 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 and starting to decelerate, emission goes into the radio. Now, I don't know if you could visualize it very well, but you can see also here in the image, I hope that you can see my mouse, because I can, but I hope that you can see it as well. In the part of the jet that is very close to the black hole, there you have the gamma and the X-rays. So the gamma X-rays give us an idea of what happens very close to the progenitor. When you go to the optical, you are not anymore very close to the progenitor. So the analysis of this optical light can tell you a lot about the interstellar medium, that is the medium around this star, or the evolution of this star. So it can tell us something about the galaxy and the evolution of the galaxy in which occur. And with the radio, we are even further away from the progenitor. So really, we can study the environment close to this massive star at different distances. I hope that this was just give you an idea of what we are studying and how we are studying this. Well, of course, with data. Remember that in research, data lead. Whatever the data are saying, we have to take it. We have to, it's not the theory that is saying to the data what they are, but we have to have something that we call, of course, that we have intellectual honesty, that whatever the data are saying, we take it and then we tune and we change the theory when it is necessary. This is why here I wanted to show you, first of all, how and why GRBs are so powerful. See, these are all fantastic HST images. And as you can see, in the among the 4 errors, you cannot see almost anything. And HST is the most powerful optical telescopes that we have. And nevertheless, we don't see anything after the GRB faded. So what this means that the GRB is just the tool that illuminated this region of the universe in which without the GRB we wouldn't see anything. So with this data, we are not only studying the GRB itself, what happens in the jet or close to the progenitor, but we are also studying the universe in parts of the universe that otherwise were not illuminated. And I think that the best way in which you can see how all this works is showing you one by one the most relevant GRBs and how they guided our knowledge of the GRB physics and the galaxies in which they occurred that are called the host galaxies. So the first one is the GRB of the 25th of April 1998. Why is this so important? Because, first of all, look how close by it is. It was just about 36 million parsecs away from us. That from a point of view of distances is rather close. And the other amazing thing was that this GRB was the first one associated with a supernova. Why it was so important? Because as I told you previously, the theory was saying that you have the two jets, and then you have also the supernova that explodes associated, the hypernova associated with the GRB. And the idea is the following, that all the energy that it is in the gamma, of course, is very bright, or the one that is occurring in the jet, is so bright that it is overtaking everything for days. Then we have to patiently wait that this light is starting to decrease so we are observing what we call the light curve, that is the brightness, as you can see here, as a function of time. So the more the time is passing, the more the GRB is fading down. And if you see bump in the light curve, then you know that that is not the GRB, because the GRB is just going down. It is the light from the associated supernova. And I would like to show you just, it is just here, this other GRB, that is the one of the 19th of December 2010, in which that it was further away. See, it was, this time it was at a ratio of 0.55, so we arrive to a bit more than 80 billion years after the Big Bang. But look, in spite of being so further away, we can still see you have the GRB, the gamma emission, I mean the one that is in the jet, that is decreasing, and then the brightness is decreasing, and then you see a bump, and that bump is associated with the relative supernova. And this, of course, was a huge, powerful method that we had to confirm that GRBs, long GRBs, are associated with supernova. For many years, there was just this dichotomy, gamma ray bars, longer gamma ray bars, supernova. And then we started to wonder, are all GRBs, long GRBs, associated with supernova? I will give you the answer in a few slides. Let's go now to another fantastic GRB. This is very, very famous. Why? Because it was extremely energetic. This number, 2.78 times 10 to the 54 erg, to you probably doesn't mean that much. This is just an energy isotopic, and it is in all directions emitted by the GRB in just 110 seconds. That is, here there is a 10 to 54, means 1 with the 54 zeros after. But if you now consider that during his whole life, that it is 4.5, about 4.5 billion years, the sun, I repeat, during its whole life, 4.5 billion years, the sun emitted 10 to 51 ergs. You see that in 110 seconds, this GRB emitted 1,000 times more energy than the sun emitted during its whole life. So these are monsters. These are the most powerful explosions in the universe, second only to the Big Bang. And now you have to start thinking that, wow, you have all this energy in such a short time, and how do you model it? And of course, this was just our free, well, relatively free lab, in which, of course, on Earth we cannot observe these things, we cannot reproduce them. So it was our lab to do radiative processes and try to see which kind of emission process can really produce these observations. And this was such an amazing GRB that if you think that it was, if it were in Andromeda, it was not, it was a redshift 1.6, but if this event were in Andromeda, it would have been in the night as bright as the moon. This just to give you an idea of how much energy was just released. And this is just how the light curve that we have, so bright in a short time. This is also another very important gamma ray burst, one of the 29th of March 2003. Why? Because we observed that this GRB was associated with the supernova, but using a different technique. Before I showed you the light curve, it is the brightness that changes in time, but this gamma ray burst was associated to a supernova using spectroscopy. Just to give you an idea what spectroscopy is, a rainbow show you spectroscopy. You have just the light that enters the atmosphere, and with the special meteorological conditions, it just interacting with atoms and molecules in the atmosphere, and what you see is just the light that is just divided in its wavelengths. Well, we use the same technique in the universe, and I would like just to show you this image. I hope that this can help you a bit to visualize. You have the telescope on the left, you have the GRB on the right, is entering a region of matter that we call the molecular clouds, with the molecules and ions and different atoms. And this light, very energetic, is interacting with these atoms and molecules. So sometimes is stripping away directly an electron, so it is ionizing the atoms or the molecules, or is just making jumping the electrons inside the atomic levels of these atoms. And once it does, we have these what we call the absorption lines, and this kind of features, these absorptions, tell us precisely which atoms this GRB met. So you can see on the left, without being too much into details, on the left you see that we are observing hydrogen, while on the right we are observing all of the other elements like oxygen, iron, nitrogen, and zinc, and magnesium, and magnesium, all of the oxygen, all different elements that are actually formed into the star and spread inside the interstellar medium once the star just exploded. And here we have another very interesting GRB, and this GRB is just very important because it is the only one for which we have a detection of a molecule, of a special molecule. This is carbon monoxide. And up to date, this is the only one in which we could observe it. And we also saw that at such a high redshift, 3.03, we have a very massive star that is also very dusty. And very dusty and gives us also an idea of the star formation rate that is occurring in that galaxy. So we're starting to put all different pieces of a puzzles together. We have the emission, we have the radiative processes, we have molecules, we have atoms around it. We are starting to study galaxies. What else can we do? And what else gamma ray bursts are telling us? This is, I just showing this because probably some of you even saw it, because this is the gamma ray burst that was so amazingly bright that was for a very short period was possible to see it with the naked eye. And of course, this is very rare, especially because it is at a redshift that is not that close by. And I have to say that it is not very easy to recognize, to reconcile the emission in gamma with what we have been observing in the optical. So this is all what I was telling you about the tennis match, in which now the observations are telling us, and we have to think carefully how to explain them, tuning our theories and of emissions and radiative processes. Now, this is one of the most famous. Why? Because this proved definitively, it was a very important proof that we can use GRBs as a cosmological tool. Because look, this GRB was at redshift 9.2, and this means that it was just 535 million years after the Big Bang. It means that without this GRB, we had no idea whatsoever that there was something there, as you can see in the middle of the image. So we had illuminated a part of the universe that we really want to study. Why? Because the more we go back, time close to the Big Bang, the more we reach the point of the moment in which the first stars were born. The first stars are, of course, made mainly of hydrogen and helium, and this gives us also an idea of how the universe was, we call it, reionized. That is how we had photons, electrons, and ions back in the universe. So this was the proof that indeed gamma ray bursts can be used as a cosmological tool. Then I want to show you this, because this is a GRB in which I worked. I am part of a very large collaboration in Europe, but also in the United States, but also in other countries, in which we take the positions that are given by the satellites of these GRBs, and we use telescopes in Chile or in other parts of Europe to observe the optical transients of GRBs to study the chemical evolution of galaxies. Now, why am we show you this? Because this is the only GRB for which we had at the same time the spectrum of this GRB as soon as the GRB just exploded. So as soon as we got the data from the satellites, and after 5 hours we observe it. And comparing the two spectra, we can have an idea of these, atomic levels, they changed. And so we can say something about the power in the GRB, and with a special method that is called the theory of the ultraviolet pumping, we can try to get the distance of the molecular clouds in which these atoms were. Here I can show you, this is what we observed for this GRB. We have aluminium, calcium, iron, magnesium, nickel, oxygen, silicon, zinc, and sulfur and zinc. And we determined that the distance of this cloud at redshift 3.5, so not close by, was about 250 parsecs. So really we can start to study the galaxy and the dust and the chemicals that are the atoms that are in around the GRB, so in these galaxies. I'm pretty sure that this is you know this GRB, because this is one of the most famous, and this is a fantastic one. Why? Because this is the GRB that the one of 17th of August 2017 that put together gravitational waves, neutron star mergers, and short GRBs. This GRB showed once for all that at least some short GRBs are in reality related to the merger of compact objects. And how are we sure about this? Because in the moment in which we observe this GRB, LIGO and Virgo gave us one of the first gravitational waves detections. You know, they got the Nobel Prize for this. So we knew, first of all, it was so close by. Look, it was just about 42 million parsecs from us. So we could study it really in details. So we could know also the progenitors, that they were actually compact objects. And not only that, so we observed that they were connected with gravitational waves. There was a merger of two neutron stars, but amazingly, we could see that for short GRBs, we had, when you see the brightness of the object that changes time in the light curve, that there was an excess in the infrared. And this is associated with something that is called a kilonova. That is just, let's say that is not really true, but imagine that if we have the supernova for the long gamma burst, for some of the short GRBs, we have an excess in the infrared. And is this true for only for the short GRBs? I think this is a legitimate question to ask, because at the moment I only told you that the long GRBs, some of them are associated with the supernova, and now we know that short GRBs, compact object mergers, that are associated with the kilonova. Before answering to this question, I want to show you this, that both stays for bright of all times. This was the most majestic and brightest GRB in gamma. And look at there, the energy emitted isotropically was about 10,000 times the energy that the sun emitted during its whole life. So this was really monster. But what we are trying to understand is that, just focus on the red part, on the red lines. On the left, you have the emission in gamma of these GRBs. The blue points are all the emission in gamma of all the other GRBs. As you can see, this is just on the top, is the brightest of all. But on the right, on the other hand, you have the luminosity in radio. And this GRB was not that bright in radio. As you can see, many other GRBs were much brighter than this. So how do we reconcile this? How it has this very long afterglows, one of the longest ever observed, for really thousands of days. We have this data. It is so energetic in gamma, and then in radio is just a low luminosity GRB. Well, there are many theories that have been shaken by this, and this is still work in progress. And I want just to conclude this with this is another GRB on which our group is working, and this was another Nature article in which we showed that there are few, at the moment, few long GRBs that are not associated with supernova, but they have an excess in infrared and they are associated with kilonova. What does this mean from the theory point of view? Well, it means that some long GRBs are associated also with compact objects. Are they associated with compact objects in different binary systems? Because one thing that we have always to remember is that in the universe, about 50-60% of all stars are in binaries, and sometimes in triple systems. So which kind of binary system this can be? This is again a work in progress. And this is my summary. This is just to to remind you that GRB is a powerful tool to study the formation of black holes, that they are associated with different kind of galaxies, that some of them are associated with supernova, some associated with kilonova, that they are super energetics, and that for sure some short GRBs also produce gravitational waves. And these are, I conclude with some open questions. And I'm looking forward to listen to your questions. And thank you.
All right. Thank you, Giovanna. This is a excellent history of our understanding of GRBs because it just shows us how many questions they've brought up, how many questions that they've answered somewhat, but still so many some questions still left out there. This has been quite a fruitful field over, I guess it's about 50 years since we were told that GRBs existed.
Yes, it was in the 60s that the Vela satellites, the secret, let's call it quotes, secret satellites detected them, and then in the 70s this was made public. And then we started to observe, but then it took time because BATSE was only launched at the beginning of the 90s, and then I started to collect data for more than 10 years. And then we had Beppo-Sachs. And then, of course, we had super fantastic satellites like Swift, like ETE, like Fermi, and our beloved Chandra that we hope that is continuing to run for a longer time.
Well, I think it also shows our audience that if the first observation of this existence of something comes in the 70s, that it takes decades to develop a satellite and develop something because we can't observe these from the ground, and that it's really kind of cool because you're watching the development of the field, and it's within my lifetime, so that actually makes it kind of interesting to me that that this whole field has grown up over the course of it. And so one of the things that always quite confused me a little bit, okay, is some of the terminology that has grown up in terms of like kilonova versus hypernova, and such like that. So just for me, who's an astronomer, could you clarify a little bit of that kilonova versus hypernova type stuff? Because I don't see it often enough to keep it straight.
Well, the hypernova is a very energetic supernova, and it is associated with that of a supermassive star. Because the idea is, just to summarize, is that you have first the black hole that is formed, then there is the jets, and here we have to admit that we really don't know how these jets are formed. This is a fantastic topic, and simulation still cannot help us very much on this. We know that it's launched, but we don't know how. Then, as soon as this is done, you have still all the matter that is collapsing, and then you have the supernova that is exploding. But to do this, you need a very massive star. When you don't have the very massive stars, you have two compact objects. And when you have two compact objects, these compact objects already lost most of their matter because they already exploded in their lifetime as a supernova at a certain point. Otherwise, you wouldn't have the neutron stars. So you don't have that much matter. So you have, when they are just, imagine that they are rotating into each other. There are a lot of very good videos about this. They are rotating into each other, they are rotating, but then they are starting to form a disk. Something that it becomes harder to keep in the other one, because with explosion you are destroying it. So you have just the disk, but you still have the jets. And with less matter, then you have that all this is just emitted cooler at the infrared.
Okay. Can you stop your screen share?
Oh, yes, of course. Sorry.
No, that's all right.
Yeah.
And now I'm going to invite Grant Justice, who is our tech support guy who avidly watches the YouTube chat to pull out questions. Grant, you want to turn on your video and let us know if you found some fun questions today? Grant? All right. Well, if Grant's not going to be there, how about
Sorry.
I have
Yep.
another question. Or Grant, do you have a question to start with first?
No, go ahead and get started. Sorry.
Okay. So one of the things I was I've never actually investigated myself is that so we know that because the distribution is all sky, it doesn't show any preference for our galaxy, so they have to be extragalactic, right? But in terms of the redshift distribution of GRBs, how is that distributed? I mean, I don't assume that they're isotropic in with distance. Is there a preferred distance at which we see the GRBs?
Well, I think this is a bit of a tricky question because there is always what we call the selection effect.
Right.
Because then we have to understand if we are seeing at the moment that many of them are just picking between that is there is a major number between redshift 1 and redshift 3, does it mean that really many of them are in this redshift, or it is only because we are tuned, we have instrumentations that are able to detect many of them at that distance? Because as you can imagine, we are observing a less number of GRBs at very high redshift.
Mm-hmm.
And so does this mean that they are less bright, that they are not there, or that we are not capable of detecting? So all this, you have to put everything into account. At the moment, we observe many of them just in the redshift that I told you. And if you want, I can show you the image with the redshift distribution. If you want, I have that image and I can show it to you. Do you think we have time for that or not?
If you got it right up available, that would be fine. I mean, it's just there are the different mechanisms that produce them, right? There are certain times that it would take to produce neutron stars or neutron star collisions, and population 3 stars, would they be susceptible to hypernovas more often than later
Exactly.
pop 2 stars, right?
Here
So,
it is.
ah,
It is not just the most recent, but as you can see, this is the one with the blue is just where we would like to study, for cosmological purposes and for galaxy evolution and chemical evolution. But as you can see, they pick a lot at 1, and then you have between 0 and 3, most of it. And the one in orange are all the ones that we detected with our collaboration.
all right. And of course, the further away they are, the brighter they have to be before we can see them, right?
Exactly.
So
Fact,
that's
yes.
all sorts of selection effects, as you said.
Yes.
Well, cool. All right, Grant,
Yeah.
how was the chat today?
Chat was lively. Had people from all over, which I thought was really cool.
Yeah, I actually, Vana, you brought in a good amount of European audience, possibly
really?
possibly because we're doing this earlier in the day.
Yes, in fact, yes.
Yeah, it's not the middle of the
If we
night.
do it at 8 o'clock Eastern time in the US, it's after midnight, and so
Yes,
I can understand why we don't get many European viewers then.
yes, indeed, yeah.
All right, so I'll get us started here. Have
Yes.
any ice cube observations been correlated with a GRB?
Oh, this is a great question. Thank you, whoever you are, for this question. I love you. And the reason is that I started as an astroparticle physicist when astroparticle physics was not a thing. I'm speaking of the 90s, and I was studying neutrinos in an underground observatory in Italy. So my PhD thesis was trying to correlate cosmic rays, neutrinos with GRBs, and the answer is no. at the moment. Well, I have to say that egoistically, I'm a bit pleased because with my PhD thesis, I said that in principle GRBs should not be the major sources of neutrinos in the universe. And so far, this connection was not found, but we found connections of extragalactic neutrinos with, powerful AGNs. So the point is that in the GRBs, you are accelerating electrons very much, but you don't have to forget that together with the electrons, you are also having protons. You are accelerating protons as well, but protons are 1,000 more massive than electrons, so you can accelerate them as much as you want, but then they will lose much more energy, much more easier. And then you know that to get in this big amount of particles, there are also the neutrons. And the neutrons, then they are very fast decayed into protons. You emit neutrinos, but in all this, if they lose energy very fast, then at that point you have the neutrinos, but probably they are not as energetic as we thought.
Okay.
This is one of the interpretations, but there is a lot going on. There is a lot of very exciting physics in this field.
And I guess we should just state for our audience who don't know what IceCube is, that IceCube is this neutrino detector that's down at the South Pole.
Yeah.
We did have a talk in this series. So if you don't know about IceCube, go back in our public lecture series playlist, and you'll find a talk about IceCube that talks about detecting neutrinos at the South Pole. Okay.
It is in very deep in the ice. It's an amazing technology advancement. It's fantastic.
Mm-hmm. All right. What else we got, Grant?
So, this will be a two-parter, and I think the answer is already known, but I would like the context from you as the subject matter expert. So one, what was the cause of the gamma ray burst that was first observed? GRB 221009A is what you mentioned. And secondarily, have you seen a gamma ray burst that has come from an unusual source or something that you weren't expecting?
Well, the first question was that what was the progenitor of that GRB? Well, we think that it was a supermassive star. It was a long GRB. We don't have anything that is giving us any different indication, but we have also to consider that in 1997, we didn't have all the amazing detectors that we have now. We didn't have all the amazing satellites that could have done that thorough analysis that instead we are doing now. About your, I hope that I answered the first part. About the second part, there are some of the GRBs that I showed you. They have a lot of pieces of the puzzle that are not there. I mean, if you consider the GRB in which you have a very, very bright gamma, and then you don't have the same brightness in the radio, you have to think what happened to the matter after a while. You have also to consider that, as I was saying, some of the GRBs could really be associated with binary systems. And there are a lot of theoretical works that are done with this. I'm speaking of long GRBs. The problem there is that it is almost impossible, considering the distance at which they are, to disentangle it, the binary system, from a very massive star. We don't have yet, a prediction, a theory that says if it is a binary system, this is how it should look like.
Right.
And with all of the first image that I showed you, this is what we would love to do it. That would be the Rosetta Stone for us. If a certain point we know this is the gamma, these are the peaks, this is the shape, and this means this progenitor. this is my dream. This is how I would like to do. But you know, many people work it in this, but at the moment it's not very easy. It is not easy at all.
And in contrast, we actually have a very good idea of what a supernova should look like, right? The
Yes.
light curve and the fall off from that and how that fades away. So, I mean, that's sort of like the example at which we'd love to be able to have that for all these other events.
But if I may say one thing, for the supernova, we know all of this because they occur in our galaxy. So they are close by, so we can really easily to reproduce, and we have been observing them for decades. But we don't have this privilege with the GRBs because, okay, luckily for us, they are far away because, you know, a GRB close by that is pointing at you, you know, I would prefer to not have it.
Well, the other thing that, your talk reminded me of is the development of the transient follow-up network of things. So, I mean, the whole development of, hey, here we've got a GRB. Quickly turn the telescopes to be able to find them. Can you talk a little bit about that, because that obviously transformed the ability to do multi-wavelength observations of GRBs?
Well, absolutely. You know, everything started when Swift went on orbit. And we had also Chandra who was there, and then they start. It was just not the end of the collaboration. At the point, it was called the X-shooter collaboration. There were a lot of astronomers from Europe and from United States, and they did this kind of collaboration in which. Now that I'm part-time, also on shift. Imagine it happens in this way. Some of us are weekly on shift. I am on shift 2-3 times a year. So in that week, I am just on call day and night. I'm always with my cell phone and the app on the cell phone that is telling me, look, there is this GRB, and this GRB has these features that belong to the group of GRBs that we decided to observe. So they are just in what we selected. It has to have just a small amount of dust, or it has to be bright enough, it has to be visible from Chile because we use the telescope in Chile. And as soon as these parameters, you know, they are ticked, then we have a program because we applied, you know, we applied to have time. So we made a proposal, we explained what we got, and we got during all these years, I publicly thank ESO to give us time. That was fantastic. Thank you so very much. And then we get just the possibility to contact people in Paranal in Chile and say, look, is the telescope available with this instrument to observe this telescope, either with photometry in optical or in infrared, or with X-shooter, we want the spectrum from this. And at the same time, if something is real exceptional, like for the boat, then we just are in contact with each other also in the night, and then we say, okay, let's put that a DDT, that is a discretional time application, either to Chandra or to HST or to JWST. And I have to thank also NASA because been very generous with us, because we could just get data. Also lately we got the data on another GRB. I cannot speak about that GRB, but yeah, you know, it's exciting, and in a certain way, you know, you feel also privileged and honored because we do what we like, and we have the honor to use all this amazing, you know, technology.
Right. And these targets of opportunity, I mean, there's building up the networks between astronomers and observatories so that
Yes,
these targets of opportunity can be observed relatively quickly. I mean,
yes,
the Hubble time and Webb time and Chandra time is very, very valuable, but they always have these targets of opportunity possibilities that
yes.
can
And
come in.
and the deal is that once it is approved, of course, we don't have any priority time. It belongs to everybody,
Right.
as it
So
has to be.
everything becomes public. That's one of the
Absolutely.
immediately without any proprietary period.
Yeah, absolutely, because this is as it has to be. Yeah.
Great.
Scientist's best friend, a scheduler's worst nightmare.
Exactly.
Oh, yes, in fact, yes. Indeed it is.
All right, Grant, we have another question on the chat.
Yeah, absolutely. Have you observed any gravitational lensing of a GRB?
Oh, this is a very interesting question because there was, honestly, I don't remember which GRB, but we thought that that GRB could be actually associated with the gravitational lensing because we could see that there were a bit of strange shapes with the different galaxies around it, but then we reobserved it. Because if it is gravitational lens, it should be there. We reobserved it and then it was not there. So, you can have your idea, you can have your observation, your theories, but then you have to do it thoroughly through it, and then you have to be, of course, intellectually honest to do follow-up observations to either confirm or disprove it. But at the moment, in my knowledge, I don't recall any GRB associated with the gravitational lens.
And I guess it would be hard to prove
Yeah.
because it's a transient event. It happens and then
Yes.
it's over. And you can go look at that field and study it and say, well, maybe there could have been gravitational lensing here, but
Yes.
you don't know where the caustics are that would produce it. So it's
And then you needed to have really something that is magnifying very big in front of it,
Yep.
and so there should be a lot of coincidental factors.
Right. I mean, statistically, you can say that some of these GRBs are amplified by gravitational lensing, but you can't point at any one and say that one is one that was done it.
Exactly. Yeah.
That's kind of cool.
Yeah.
Nice question. I'm not seeing any more questions. Are you, Grant?
Nope.
Great.
Questions are
All
dry.
right. We've had a wonderful conversation here. We've learned almost the complete really, we've learned the complete history of GRBs here because it really is a 50-year field, which is wonderful to be able to sort of compact it down into a single talk. So thank you for highlighting all those very important GRBs that happened over the years. Look forward
Thanks to you for having me here.
I look forward to seeing where we go from here.
Yes.
Where we will go with this speaking lecture series is that next month, May 7th, Stellar Astronomy in Search of Dark Matter. We hope to see you here for it. Thank you all and have a great day.
Thank you. Bye.